So I'm here. I'm Flip Phillips from Motion Picture Science. I'm here to introduce today's speaker, Ed Granger. Ed and I met 30, 40. We were teenagers, both of us.
He was a teenager. I was 40 years old.
Okay. And when a friend of mine from Pixar, Rob Cook, left, and there were a bunch of us that left, and early on in the Pixar days, I went back to graduate school and I needed something to do as a break. And Rob Cook, who has started a company called Lightsource, and one afternoon, this guy just shows up directly from Kodak, moved. I get, what do you say? Quit on Saturday and moved in on Monday, kind of thing.
Sure,
Yeah. And so, so I've known Ed over this time, just as, like I say, we worked on project together. We built the first, this was the first kind of prosumer colorimeter that Ed designed, and it's kind of a piece of, anyway, but it worked.
It's a good boat anchor.
It's a boat anchor, yeah, but it was fun. Ed is the president and has been for several decades of Ontario Beach Systems, which I only recently learned Ontario Beach is here. I thought it was in California, and then I thought Ontario, and yeah. So anyway,
Seneca Park.
yeah, yes, right. It makes sense now to me, but not when I was. Yeah, IQ Color, Universal Color. He's got a bunch of subsidiaries. We met at Lightsource, which was who created this thing, and was eventually sold off to X-Rite. He got his PhD at U of R. He was a distinguished professor, and I didn't realize this was the actual department, but printing management and science here at RIT. He has been a professor to some of you, a colleague for some of you. He was spent most of his time then at Kodak, left Kodak to go to Lightsource. He has more 40 patents, 80 pubs. He's an SPIE fellow. Creator of the ATD, then QTD, and now HAB, perceptual uniform color spaces, which I think we're going to hear about today. So,
and I'm also Who's Who in America.
Oh, he's in Who's Who in America too. So, and with that, so I introduce you to Ed Granger. Yep. I want this back. This will be worth
okay
someday.
I hope you can all hear me. How many people have a camera in your midst in hand? What I'd like you to do, just to introduce this whole thing, is have you all take a picture of the crowd, and then after you take a look at the picture, and then look at the crowd again, and that's where we'll start talking about the new basis of color imaging and so on that we're going to introduce you to, which is basically what it comes down to is everything they talked about color, that's what I'll forget, please. And we'll start over again. So if you take a picture, now take a look at what your picture looks like of the room and so on. And then look at what your camera recorded. Okay? Look at the heads and so on. What you'll find is that your perception of the room and everything is not linear.
Because if you're gonna wonder, we'll probably have to put a lapel mic on because we've got people online.
Oh, no problem. Not a problem.
It's working, so I usually.
Good morning, Robert.
Oh, Ed, good to see you.
There you go. See a little better than that.
So one of the things I want to show you doing that is that our perception of the world is not linear. And so we're going to be talking today is basically developing a new system that basically is a analog. It's a new space that is completely orthonormal. And in orthonormality, it has to do with wavelength, saturation, and darkness. And out of that, the new model allows us now, as we'll see, to be able to use this model to actually be able to absorb anything from color, using Crayolas, water paints, or anything, to put them in this space and actually see how they would look to a person actually using these things. So if you're saying, I want to have an image here and I want to basically do it, the thing I want to be able to do then is have a space that I can work with that actually lets me see the color differences and everything but not using the current color difference technology, okay? And what we're gonna show is most of all the color difference formulas are wrong. And so at the end of this, we're gonna just put the computer up and bring up something, so anybody who's interested can come down. And what it is it's a tool we built. So it has all the color spaces in line, and what you can actually see by running it is, it allows you to choose what wavelength you want to be at. It allows you to choose, you know, how much saturation you want of the color, and how much darkness you want of the color, and then what tolerance you want for the color. And what we demonstrate with it is that all the current color management tools fail. And the new one we offer does not fail. Under all those conditions, it never fails. And so this is one of the things we're offering, saying we have to rethink what we're talking about in terms of color vision and tolerancing and so on. And so what we're looking at is how the human vision system works and so on. So let me get to what we're doing here for a minute. So is this working? Supposed to be able to hit this here and hang on a minute.
Right here.
I did that. Well, I know what we're not doing. We're not, I know what we have to do. We gotta start the show. We actually, are we started? There we go. Oh, what is it?
I'll do it for you.
All right, okay, all right. So one of the things that happens is started this whole thing way back in the 1840s is Grassman came up. And the big thing he realized was the fact that human vision at the early stage is all linear. All of it's like we're doing logarithm vision and all that. And it turns out, no, Grassman actually put the very first thing as the basis, as it says here. I don't have to read it for you. It is the basis of all modern colorimetry. Now, one of the problems with colorimetry was in the past, when it was defined in the 1930s, we didn't have digital computers. So we had these things. And in order to save problems, the CIE defined these curves. Why? Because people using those computers at the time had to put in all this data manually. And they didn't want to have people have to think about having positive and negative numbers to be added. So they made the whole thing so that when you're on a computer, you could do your computing by just simply tapping on the keys, not worrying about whether it's a positive or negative sign. Is this a good solution? At the time it was. Next slide. Okay, what's the problem with the old way of doing it? And what it has to do with the whole thing having to do with the coal house problem. And the fact is, what happens is that the whole thing about the definition of why and not taking into and saying that color was not there. In other words, the whole thing about having definition of color, you said, okay, I had Y, and then I had these two other things called X and Z that they really didn't quite know what to do with. They actually almost threw, all they did, X and Z did for them was to give you a colorimetry diagram, but they didn't seem to have any appearance in color. And what we're going to show, of course, is the fact that they do. So in the new system, our gray comes out when we say it's an L50 with QTD. Notice that it matches the blue in our system. So when we say that we have a blue of L30, we actually come in and say, well, no, this is what over here, this is what colorimetry today would say is that would be an L30. But actually in our system, it turns out that it's not. It turns out that the grade that we have at that level for QTD matches the grade of the actual apparent brightness. So what we've done is actually then say all the things having to do with basically the problems of the HK effect and others go away. So these over here, I'm not going to read it for you, but anyhow, what we've done is gone through all the things that we have that affected people in color vision. And now we have brought all of this from painting and from pointillism and everything into one basket, you might say. And so as we go here. So this is our model development. So what we found was that instead of having a whole bunch of vectors and everything, we found we had a very way of coming up with, in the human visual system, at the base of the brain here, there's a lateral geniculate body. Lateral geniculate body is organized that it has one vector that literally is for luminance only. The other vectors, red, green, yellow, blue, it has actually 8 different mechanisms. So they have red versus green, green versus red, and they could all be made into a new vector. So what we have then, when we do pick those vectors, we come up with a new diagram that looks like this. That's our diagram. Doesn't look like any diagram you've seen, but now, if you look at the stuff that had been done by one cell, you can see that by actually using the new system of taking into account the actual actions of the human visual system, that now using this diagram here where colors are actually equal, as you can see, we also reproduce with a R squared 90, the actual actions of what one cell and so on found for the human visual system. And a little bit of jogging here, as you see, is actually an error in Mansell's measurements, as it turned out, really. And this is now where we went to, where a friend of mine basically went and actually is a scientist who basically worked out, went in and measured the actions of the human visual system at the LGN, back of the brain. And that's where we are. And what he found was that there once again were these 3 mechanisms. The upper one is what he measured for the black and white channel. And then the other ones are the blue yellow channel, and then the red green channel is the blue one. And so, so T is red green, D is of the blue yellow, and Q of course is our brightness. So now what we did is then model that, and by looking at the macadam ellipses, what we found was, as you can see, that QTD in talking about color differences and so on, really our ellipses that we make and so on in macadam space have the least amount of deviation. And you can see where, unfortunately, delta E2000, the way it's done right at the moment, doesn't model color difference at all. They basically are a factor 2 smaller by definition than what the actual color differences are in the human visual system. And here's what that looks like. So here's our new system, our universal color system company has our QD space. Here's what it looks like, and you can see that the actual lab, our macadam ellipses have a deviation of about 1.6, and you can sort of now start seeing what's happened where you need so many. We only have 4 equations, and next slide, there it is. Here's a comparison, and there's an old thing, Occam's razor would say, well, if I over here, I have 5 equations, over there 22. You can see the eccentricity of the ellipses. We have a saturation support. The big problem with LAB today is it has absolutely no saturation support at all. It is basically missing. And it's the reason because when they take their A and B components to actually compute delta E, they take the lightness times A and B to give you the color difference. And what that means is that there is no actual support in LAB. So as you change your lightness, it turns out that A and B changes without there actually being a physical change or a mental change in the actual color appearance. And so one of the things is that you can find out things that's not consistent with LE. We have all linear calculations. They're not, and you could read the whole thing, but the whole thing is that what we found is that the current specifications for color and everything in LAB and so on are really missing quite a bit. Let's go to reproduction. Okay. So what we're doing now is we're taking our QT linear space, and now what we're doing is we're going to model it into a cube or into a brick. On the face of the brick, what we have is wavelength going this way. Going back on the top of the brick, we have saturation of the color, whatever it is. And then now in the brick this way, we have basically lightness or darkness. So think of that, this becomes then a universal brick. And the neat thing about the new space is that that brick is basically an analog to all color. So if I'm doing a rendition in watercolor, we put that information into this brick. And then when we reproduce a picture, it shows us exactly how that picture will look in watercolor. We can do it for oils, we can do it for anything. So with this one universal brick, we have a way of predicting what the color error is going to be and exactly how to reproduce anything from any point of view, okay? And so what we do is, we're really not going into a lot of the crazy, but so HAB is a new thing. It's a color brick, and basically it does this. Now we can go to another thing. And here's the top of the brick. Somebody made this thing up. So actually, that's how the color is actually stored in the. And now, when you say the color is stored there, that color rainbow can be made by any method you have. You can set it up so that rainbow, when we started, for actually seeing how the color picture is going to happen, you make that rainbow with Crayola, with watercolors, with television or whatever, and it then tells you exactly how it's going to reproduce on the device that you have. And we do it at grayscale. It turns out that Grackle right now is asking you to use a lot of color ink. This is the current Grackle standard that's being used for graphic arts reproduction. Now, what we've done is to change the whole world and say, wait a minute, this uses a lot of color ink just to make black. Let's get rid of it. And when you do that, you get this curve over here. And what you're doing is basically here, we're using the ink just into it to get to about 8% gray. And then from here on, we're doing is adding mainly black ink. And what these do here is they basically doing the interpolation, so we get not 0 to 100, but we actually get 0 to 256 color. By actually using this, we actually get better color definition, and we basically use, as you can see, quite a bit less ink. And the only thing that as we turn up at about 60 or 70% darkness, we then start bringing in the ink to give us a density to black at the end with most inks. So anyhow, now the next thing is that we're doing is everybody's heard about Dolby. And people have seen some things having to do with Dolby. So what we found out was that we can use a brand new set of, with our model, since we separated darkness from chroma, we can now actually use the darkness with these curves here. And so with a simple polynomial that I've invented, we can actually expand the dynamic range. And here's an example. This is the original. This is what Dolby does with the image. And over there is what QT does with the extended dynamic range. One of the things that we do, which is very simple, it's some work that Mark has been doing here, is the fact that we actually hold the color, as you can see, throughout the picture, while modulating only the darkness and lightness of the picture. And by extending the range in the bottom, at the bottom end, we're using a lot of black, we're actually expanding the bottom, and let's go to the next image. In the next image, what we're seeing is, this is the original, and then that's HDR. You can see what they've done to the barn. They've washed it out, sky. And now with QTD, actually with our mid gain picture, you can see we've preserved the color of the barn. We've made the image actually look more colorful, more bright. And actually it preserved all all the chroma, the ink and everything in there. Look at the grass, more definition and so on. Next picture. Now this is high key. Once again, using our factors, this is what HDR are doing very poorly in the light part of this definition. And by using the lower curve, we take this picture and that's how it comes out in the image. So what we're looking at is by using the new system, basically we solve all the problems having to do with of color density. What we're doing here is we're maintaining the color, but we're changing the grayscale in that brick. So we're doing something very new. So we're not scaling only the black, but by keeping the color, we keep the dynamics of the picture in color, while actually compensating for compensating the dynamic range to bring out more of the image in each of the ranges. So in printer, you can see what we're doing in printing. Let's go on. Now, here's what we're doing in the graphic arts. I mean, in television. On this side is our new 8-bit image. On the other side is now Dolby Vision 12 bits. This is photographed with a 16-bit camera. And so we have all of the, so, and now what is the limit in terms of the display? You are a 6 3/4 bit, receptor. What the hell is 12 bits doing for you? And it turns out nothing. So over here we have the 8 bits and we have the former ability to adjust for keyness of the image. Next picture. So as a function of keyness and a function of what you can see how we've held the color. I'll change it. This is 8 bits. That's 12 bits. Photographed off a screen with a 16-bit camera. Next one. Okay, same thing here. You can see by using the bits correctly, we basically don't have a real problem. Next one. Once again, see how they actually saturate the colors over there and lose dimensionality of the tubes over here. So once again, by actually using the color in 8 bits to actually explain or using our new dynamic range model, we can actually get at 8 bits much better pictures than you can. Another one showing, look at the island, the airplane, all the things that you see basically in terms of color on the airplane and everything. 8 bits, 12 bits. Next one. One of my favorites. Once again, look at the lights in the background and how we bring them out, especially. So what we're saying is that in the images, we basically keep the color, we change the darkness in a new way so that they're not coupled. And we basically get images that are actually a little bit brighter and a little bit more definition. Now here's a picture that is very difficult, but look at the color up at the dashboard there versus here. You can now see how by keeping the color separate from the dynamic range of the blackness, we now can do something that has never been done before. And that is in terms of picking up the dynamic range and maintaining only in the darkness and not in the chroma region, we can keep the chroma of the picture saved and also adjust for the brightness. So what you see here, particularly in this region and up in the dashboard region, you can see how the new model basically preserves chroma and in a difficult image like this. Keep going. Once again, and here you can see what happens in the red region in its overall color. Once again, they have 12, we have 8. Next image. Mondrian. Once again, look at the colors and the dynamic range. Look particularly in the blue over there. You can see that what we're able to do now is keep the actual color differences and bring them out. And by modeling the black level to this new method, we basically can now get more dynamic range in the color and actually compensate for the dynamic range in the black to basically show you more of the image content. One of my favorites. Once again, when you look at the rocks and the color, the chroma, that's 12, this is 8. Look at the color in the field, color in the rocks, the overall brightness difference. Which one do you buy? Let's go. Okay. So this is what we're looking at right at the moment, is the fact that this whole system is allowing us to do much more in terms of color for print and for television, for any display, by using this new system and using the color brick. It turns out we can now accommodate any color system. We can, accommodate any of the keenness of images in a brand new way that keeps the color, modulating only the black. It turns out we get basically much more dynamic images with only 8 bits. So the color savings in television and so on, and the reproduction is actually, let's go to the next thing.
That's the last slide.
Hmm?
That's the last slide.
That's the last slide. Okay, so we're open now, and we have some images over here for later on you can look at. Okay, we'll open up the questions and see what you guys have to say. Anybody got anything? We can go back, look at anything you want to see. No questions?
Well, on the one picture, I clearly saw it looked like back on one more.
Oh,
Keep going back,
oh,
right there, no, one more.
okay,
Oh, that wasn't it.
okay.
There was one that right there. You can see.
You know what that is? Our shield on the window opened up and we didn't know it.
Oh, okay. So that's what the one you saw
No.
more definition.
So what you're looking at, we had a black curtain and somebody bumped into
Oh, okay.
it. Terrible.
And-
Go for it.
In the beginning, I don't think you explained to us how you come up with the QTD dimensions,
Oh, it's basically just
because the XYZ.
it's a parametric, vector transformation. So I took the normal color space and then transformed it from its dimensionality to a unit dimensionality. So in a sense, I took the spectrum from red to blue, so to make that a unit. We took chroma, made that a unit in our space, and then we made darkness a unit in our space, okay? And then, so that was I didn't go to any mathematics. Anybody that's really interested in this will give you all the mathematics behind it. But to do that in a talk doesn't work.
Yeah,
So, but anyway, what we're really doing by going from real space to the brick is showing that in terms of reproduction and everything, we keep basically the critical points of the image, we keep the color, we modulate whether it's a low key, mid key, or high key using our curves and basically by doing that, we basically handle all kinds of images. And by doing it, it allows us then to make images in any kind of system, whether you have watercolors or whatever you want to work with. Tells you how the new system will help you get the best dynamic range and the best color out of an image by using this new system.
so when XYZ is created, there's a lot of adjustment to too much luminance to
Well,
the white channel.
where you see XYZ is an excellent way to specify color. It's a very poor way to basically talk about how your image is going to look. It leaves XYZ and the lab system basically is a very poor system for actually doing color rendition, particularly in the blue region. So the Helmholtz-Courage effect and things like that, and the Abney effect, and so on, are all aspects of using LED and the XYZ system. Okay? As soon as you get rid of the XYZ system and what's actually happening with the lateral trajectory body, then you get answers that really add up to how the vision system actually works. Okay?
I agree with that, and I like the fact that in your results, I can see that you have a pure separation between lightness and chroma, kind of, so you can manipulate lightness without affecting the chroma
Yes,
saturation aspect.
Absolutely, yeah.
So I just wanted to know, like, how this separation come into play in your space?
And what?
How could you get this, independence?
Oh,
between,
because what happened was when I went to the HAB space, I made colored, from red, from blue to red, independent. I made saturation independent, I made darkness independent. So they all of them are independent. So what you have now in my program, for every wavelength I have I have a saturation and darkness for every wavelength in the color system. Okay, it's a little bit, we have computers now, it's a lot more data, but we can actually do more with it now. So our brick basically is made up of 256 slices color space, where we use our model to get an orthogonal space, okay? Anybody else?
The whole objective is to make the reproduced image look like the real
Yeah.
object.
Yes, that's right. So we're trying to make everything like using our new transfer functions for low key, mid key, high key throughout everything. Actually, to mimic how the human visual system actually accommodates these images when you look at them. So if you have a low key image, what happens is your adaptation system goes to the dark end and opens it up for you, even though you don't realize that's what's happening. So what we're doing actually is modeling most of the features of how the human eye handles light and color, okay?
But you don't need any of the characteristics of the detector system.
No. Actually, that's the whole thing about going to the cube, is the fact that we're doing is we've got a normalizing space that allows us to use any light source, any television to any color metric system. So we put it into the system, and basically what it does then is to normalize everything and show you the optimum picture that you can get if you use our system, okay? Anybody else? Now we have some examples over here of how the system works in print. And actually some new things that we're doing basically with how you make gray dots on paper. So we're finding out the complete new way of doing that also, yes.
So if you say the goal is to make the colors look real, do you say that necessarily the image will look better also? If
It actually, if you look at what happened in some of those pictures, like where we had the car and all that, what you find is we actually keep the chroma of the picture while modulating the black and white. So what it actually does is, out here in the hallway somewhere, Mark has got a picture where he did all those things with different layers. This simply actually does that same thing, but with curves, okay? So what it's actually doing is modifying how color and brightness is used throughout the volume. We're using now our new magic curves, actually. So we're actually modeling what Mark Kershaw was using his method, but this now actually puts curves in and actually does his method with the actual curvilinear spaces. So what this does actually cuts the cost for both television and so it means that television no longer needs to be 12 bits. To show that because of the human visual system limitation, 8 bits is enough if you use our color appearance model. John?
Has anybody started to use this commercially?
No, we've been holding this under our hat. So what we're working with the university here for is to actually give the science to the university and then start the whole monetization process in the university. So in essence, the money I want to monetize basically the university for research. So it's not my money. Okay, so we feel that this is enough of an advance in science. But in terms of what's the one thing that's going to make somebody adopt this? Money. So what you find out in making a television set, if I no longer have to go to the complication of 12 bits or 10 bits, you go to 8 bits. And all the mixing that has to go on right at the moment goes away. It turns out that the cost of making the computer to run the display is about a half of what it is now. the number of components and everything go down, and the picture looks better on the screen, okay? And in print, we basically have reduced the cost, I have these samples over here, everybody can take a look at it. It reduced the cost of printing by a factor of 2. Okay, and basic, the color and dynamic range of the pictures goes up. And even more than that, we come up with a brand new way of doing half-tone dots and so on. That really, all heard about stochastic printing, using the little dots and so on. We've come up with a brand new way of doing stochastic printing, using actually ellipse form. And it means that there are no longer, you can actually use all the old rules for, dot gain and all that with our system, because there's no screen angle in the system at all. The answer is there's no array. The color coming out looks like it's been pointed, and the head looks like it's been painted. It is actually uniform. You don't see any screening. You don't see any interference. There's no more dot, little dot interferences and so on. They're all gone away. We have 3 black dots and we have 3 white dots. And you can pick, so the guy comes in, says the first one picks black, he picks one of the 6. That's kind of like, so this guy comes in and he's got 5, he can pick one of the 5 dots, either white or black. Next guy gets to pick 4, next guy gets to pick 3. Okay, that gives you just a net dimension, 320 different style dots that you can make that don't interfere with one. So instead of having moire anymore, what you see basically is just the dot patina in the picture, okay? So if you go over, we have them setting out over here. So anybody who'd like to go and look at them, go and look at them. We have the whole thing showing how we do the new half-tone dots and how we do the actual replacement of color with black. And you can see that the pictures, particularly in terms of where we're doing both grayscale, making pictures larger, and actually doing things. So the second picture is showing how we do brightness. The fourth picture is sharpening and brightening picture. And what you can see is basically in doing this, there is no color error induced. All you see is what you wanted to get. So as you look at it, what you can actually see is that there's no, what this does is it takes out all the problems we call it. On reproduction on press, using our system, you can run like 64,000 copies out of press without there being anybody having demand press at all. The system has great capability for tolerance because we orthogonalize it. It turns out that there's great tolerance to press variation. There's very little interaction between the color inks and the black inks, and so on. So it turns out that in terms of presses, you basically cut your paper waste by a factor of out of 34 sheets, 1,000 sheets. You don't have to, it cuts out the waste of about 5,000 sheets at startup. So at startup with our system, you get within the first 2 or 3 rotations, you get saleable color, unlike other color, just like you would after 4,000. So the beauty of our system being independent is that on press, you basically don't have any free stuff you have to do. The press run is stable for the entire press run without any of this attention. And in television and so on, the thing is that we're doing is it basically gives you better color. The fact that you can now have system adapts to, it's not just what happens in HDR today. You have one transfer function. The new system basically has the ability to, as you saw, to basically dynamically change. So if you're making a movie, you can actually have basically as you go from frame to frame. If I'm showing one scene, I come here, I change the dynamic range that I'm using for the next scene. So if it happens to be a low key scene, okay, we'll do that. This happens to be a high key scene, we'll do that. So it actually, in terms of doing movies, in terms of doing and printing and so on, what you're always doing is giving the viewer low cost. So we're taking out all the coloring that we can. And in movies and so on, what we're doing is having the ability to actually adjust the basic current gain of the image. So if it happens to be a dark image, a cat in the holding type of thing, we'll adjust the image for that set of frames. In the program, it actually knows when the frame color and everything needs to be changed. So when it comes to a new section on the first frame, it changes what what operation used to display that image out, phone and stuff. Anybody else? Yes, come back.
So, in HDR standards so far, they teach that like for normal, standard dynamic range label, 8 bits might be enough, but if you have really high dynamic range, like darker, blacks and, very bright highlights, have you tried your, space for that with 8 bits?
Well, actually, what you saw in the barn image, that's what we actually get there. There's, the barn was pretty much looking at a range that was low and high at the same time. So, and the thing that really makes it is the fact that what I can do then is to modulate the black image versus the color image. Remember, we keep the color of the barn, you can't do with actually the tools you have today. So the neutral, they're independent. I can keep the color of the barn, which then sends to the system, even though you don't use very well. How does that work? What it does for you is by keeping the color separated from the lightness, you're gonna adjust the lightness, keeping the color, and it allows us basically to handle high dynamic ranges in that manner, okay?
You don't see any, quantization artifact?
No,
with
you never see quantization error in this system, no, never. I mean, we've made it so the color and everything is not 0 to 1, it's 0 to 220, 0 to 225, okay? And so it gives a range for all the adjustments we made without any kind of quantization at all as we go through. We very carefully made it so that that was the first thing we looked at. Where we need to, and each of these pixels to make sure that we see no quantization, period. No matter how we adjust it, there will be no quantization. So that's we're going to draw through. Each dot is broken up into a 15 by 15 cell. And each of those 15 cells, then we have either an ellipse or we have, and then so we have, you know, dynamic color happening, okay? So this is basically a brand new way of looking at that whole thing, going to the color cube, which is our basic sort of like color standard for all imaging that allows you then to basically produce optimal images for any impact, whether it's red, green, blue, or whatever you want to do. So that's the whole point behind this, is it gives you, it solves the high dynamic range problem simply, and it also solves all the things having to do with, well, what does the thing going to look like if I use Crayola or I use watercolor? That all can be now just put in the HA plane, and the rest of it then is history. It'll reproduce the image optimally for whatever color system you use. And thank you again for the time.
Say hello. Yeah, like come down there and say hello.
Oh, yeah.